Okay, year 12, feedback on the superposition test. There were some great answers, but this was actually quite a hard test and quite a lot of the answers didn't have quite the right detail to get the marks. So according to the mark scheme, quite a lot of people lost marks here and there. So overall, most people had issues with these two things. Okay, it's using terminology in the right way. And the crucial other bit is the questions were slightly, not necessarily standard, they weren't tricky, but you actually needed to answer the questions, and some people were trying to give a standard answer rather than actually answering the question. Okay, so I'm just going to pick out on the main things rather than do all the answers or anything like that, and really pick out on several key points. Okay, so the first one is we're looking at two types of standing wave. Okay, we're looking at that, superposition. One is the standing wave, okay, where you've got something like a string or air, so it could be vibrating that way or it could be vibrating longitudinally, it doesn't really matter, but it's this idea of what you can detect. So if this was the string, you could see where it is, that would be your observation. If it was sound, it's the volume, it's the loudness. And if it's light, then you've got this idea of brightness, etc, etc. So it's how big is that signal, that maximum point and that minimum point. So for this one, you've got the terminology for the biggest vibration, which a few seconds later is a bit smaller and all the way through. Okay, so there's that part, but you've also got that part. So you've got your node and your antinode. They have nothing to do with the idea of ripples spreading out and interfering. Okay, so people got mixed up between the two types of questions. There's similarities for sure, but these are two different sources. Okay, source 1, source 2, producing ripples. These can be different sizes, they can be different in all kinds of ways. This one is made from one wave that reflects back and forth. Okay, so that bit was one of the problems. We had the right words for the wrong answers. Okay, so just make sure we're using those in the right place, and we'll pick out what we're after here. So I will not do full sentences or anything like that. I'm just going to pick out on the main things. So most people would have got 2 marks, but they were talking about, again, the wrong word. So what we're after is not displacement, because displacement changes as this vibrates up and down. The displacement is changing all the time. So we're actually after the biggest point of the biggest displacement. Okay, so this is where you've got nothing happening, not precise enough. So no vibration is fine for that one. That's what we mean by that. No energy, yeah, try and avoid it though, because you can't really observe energy. So no vibration, or no displacement, or no amplitude, all of those are correct. But for this one, you definitely need the idea of maximum, which most people got, but it's amplitude. Okay, the maximum displacement is at its maximum. Okay, so for that snapshot there, all of that part of the string has reached its maximum amplitude, maximum displacement, i.e. has reached the amplitude, but some amplitudes are bigger than others. So the antinode is at the biggest amplitude. Okay, it's the maximum amplitude. So that needs to come across clearly. Okay, and actually just putting those 2 words is all you need to go really clear. Generally good. Some people didn't do that. Okay, so again, answering the questions, some people put some labeling. Okay, but be wary that it can get knocked down. You could just take it from there. Okay, node and antinode, that's nice and clear. So a little bit sneaky, but yeah, it asks you to draw arrows, so just be careful. Okay, state, no problem with it. I don't think anyone got that wrong. It's 3 because you got 1, 2, 3 lumps. Okay, so that's fine. And then this is where it fell down a bit. So a lot of people jumped into that, which you need. We have our frequency and we're after our speed. So it is V equals F lambda. no problem with that, but that is not the wavelength. Okay, so that crucial bit, don't forget, is that each node to node is half a wavelength. So you've got 1, 2, 3 half wavelengths. So you can do some maths, or you could just use mental maths and just go, well, that's 90. So then for 2 half wavelengths add up to 60. So lambda equals 0.6 meters. Showing that clearly somewhere is one of the marks, and the rest depends on that. Okay, and then the rest works through, no problem, stick the numbers in, it's okay. Okay, part C, challenging question. Okay, now what they're doing is doing two different things. So we have the speed of the wave and we have the weight on the end. Okay, so if the weight changes, things happen. What a lot of people did was just looked at that as an equation and tried to just play with the equation. You didn't think about what was happening, or it wasn't coming across. So what we're after here is there is some multiplying factor, and we've mentioned this in a lesson, but that doesn't matter because it's not on the spec. But it's the way they ask it. So they've got two variables and a constant. Okay, it says it's constant for that string. Some people calculated two different values, don't know. So when you've got a certain weight, okay, when it is on for part B, okay, so in this question, that means with that thing on there, okay, and we will need the answer. So you need to actually find out what 120 times 0.6 is, which will of course give you 72 meters per second. Okay, now you've got the units there, but I'm just such a habit of putting it in. What they're after is trying to see if the wavelengths will still fit in that space. It asks you to say whether you'd still see a stationary wave, question mark. So would you still fit? Doesn't mean it has to have 3 nodes. You just need a whole number of nodes. Okay, so what we're after is actually trying to swap it around a bit. The thing that's making it oscillate, okay, the oscillator still is 120 hertz, so that's fixed. Okay, you change the mass on the end, change the weight on the end, and therefore we're changing W. So what I would do is, the easiest way is K is constant, so that is by far the best way of dealing with it. Okay, find it by rearranging the equation to make the constant the same. And actually what you'll find is for the first velocity and first wavelength, it will of course equal the same constant for the second velocity and the second, sorry, not wavelength, weight. Okay, so for weight 1 you'll get a certain speed, for weight 2 you'll get a different speed, but how do they fit? So what we want to do is kind of just look them around like that. So we've got our 72, and that is with the square root of 4 on the end, which everyone spotted was of course 2. Okay, so well done. And then what you want to do is you want to find the new velocity, okay, under with root of 9 underneath. Okay, and if you do that, what you'll do is you'll get a completely different speed. Okay, so that on its own doesn't tell you anything, but what it does mean is, and again you can work it through, so you can do it in steps. K is 36 if you want to do the maths, so that equals 36. 36 times 3, okay, that will give you a new speed. So your speed has gone up by 50% if you want to think of it like that. But what you're after is the wavelength. So, excuse me, it's the new wavelength, okay, will be the new speed divided by the same fixed frequency. Okay, and if you do that, what you'll find is an exact number of wavelengths will fit in 90 centimeters. Okay, so that is what we're after. It's a difficult question. That is a difficult question, you can tell, because it's giving you something that's not a standard equation. Okay, But that's the process with anything with that some unknown constant. You could have got 1 mark just by working out k, okay? You could have got your second mark by finding out what's happened to the velocity, even if you don't answer the question itself. But it's all about the idea. Things change, but will the wavelengths, whatever they are, will they fit into that gap? Okay, because that is fixed. Those are bolted down. All right, so quite a tricky question. And then maybe because it was squeezed on the bottom and the top of the next page, it was a little bit confusing here. So if I could just go back to my diagram, that's interference. This is what's happening here. This is, shall we say, superposition. I mean, they're both superposition, but they're different things. That is not interference, my diagram at the top. So what you actually have in this one is your waves have to meet. They have to overlap. They have to collide. They're not hard, so you can't actually collide them together. But basically, the 2 marks are for the waves. It says 2 waves. So 2 waves meet. If they don't do that, nothing happens. Okay, so it doesn't need to be difficult. You need to explain the meaning of that. So where, let's put it there, where 2 waves meet and superpose, okay, that is actually just the first mark. So just saying they meet, just saying they superimpose, or putting both together is still only the first mark, because it doesn't actually say what interference is. It only happens when they meet, but what happens? Yeah. So what you're after with this one is the fact that when they meet, you've got a process going on, which is that they actually add together. Okay, so there's a what it actually is. So displacements add up, or displacements, keep it simple, adds together. Okay, so that is the crucial bit. That's what interference is, but it's made of 2 waves meeting, so you can't have the second one without the first one. All right, that's crucial, whereas this one was a bit easier because you've actually only got that one statement. Okay, so coherence, large number of people got it, well done. They don't need to be in phase, they can be out of phase, but they're not changing phase. So the whole point with that is it's your waves are at constant phase difference. And those are crucial for part B. So some people ignored their answers to part 1, but you know, it's all part of the same question. So do please notice question parts as you're going down. These 2 go together because they're in the same section. Okay, they're all about it. Sorry, saying 3, all about this thing up here. So, crucial bit. A lot of people badly wrong on this. You don't need a lot of words. Okay, it's about saying what's going on. So you need to mention path difference or phase difference. Okay, without doing that, you won't get the marks. So that's crucial. And to explain how. So quite a lot of people said you will see this, or you get this constructive destructive interference. Yeah, but that doesn't explain how the pattern is formed. Okay, now you could try and describe and explain what's going on here, but it's easier to describe what happens, what you see on the screen, or here, sorry, because it's loudspeakers. So you're going to have your central bright fringe. No, it's sound, but it doesn't matter. First, second, etc, etc. Okay, so the first fringe, so loud, loud, quiet in the middle, quiet in the middle. So that's your pattern that you're trying to explain. If you put it on the diagram, they know what you're talking about. So nobody labeled anything up. A few people try to draw stuff in here, which can get a bit messy. All right, so don't try and draw the ripples. You've seen mine, they're bad. If you got this, and again you can label it on here if you want, that works out. So these are constructive interference. Yeah, So is that. So that's crucial in your answer. You need that phrase. That is what you're seeing. You're seeing the fact that the interference is adding up to a bigger, louder sound. Okay, so constructive interference doesn't say what you hear. Okay, you know, constructive interference is loud. You need that connection there. Okay, or bright if it was light. In the middle, you've got the dark bits if it was light. So here we've got destructive interference. Okay, and also in there, and also beyond. Yeah, so spacing out, you've got your bright or loud spots, and then you've got your dark spots in the middle. All right, so that's the pattern you're trying to get across. You've already started to give a hint to your answer there. So does it mention this? No, so it doesn't explain how it gets there. Now, a bit of a mistake here, just really for the 3rd mark. So some people gave some great answers but only got 2 marks because, or if it wasn't quite so great, didn't use the words enough, you only got 1 mark because they just described one dot. Okay, so here the waves are in phase. Great. Here they are also in phase, but they're in phase differently to they are here. Okay, and you're trying to get an idea across that's quite general to go together. So something like at, you know, I would start backwards with your observations, is easier. So at loud spot, yeah, you get constructive interference. Again, don't just put arrows, but you're making it short for you to have a shorter video. Why do you get constructive interference? Because they are in phase. And some people try to talk about these changing and stuff. No, they're steady. Okay, you are moving a detector along here. You're not changing anything about that. Okay, it doesn't mention those being changed. So don't assume stuff, don't make stuff up. Okay, so in that case, what you want is, why are they in phase at every loud spot? Okay, and the reason is waves are moving up and down together. Doesn't mean they've gone the same distance. So the because bit, that's your explanation, because it's got a because in there, because it's travelled, or path difference, depending how you want to put it, but path difference is equal to a whole number of wavelengths. Okay, so it might have gone 3 extra wavelengths, but they'll still arrive in phase. 2 extra wavelengths, the same number of wavelengths, but a whole number. And without that mention of different numbers, you're not going to get that higher mark. Okay, so don't just say they're in phase because they've travelled the same distance. That would only be that dot. Okay, or one has travelled 1 extra wavelength. That would only tell you that dot and that dot. It wouldn't tell you the middle one. Okay, so you're trying to get all of it together. Okay, so it covers all answers. And the whole opposite with the other one. A little bit harder to explain this. So the whole idea with quiet, well, that's the destructive. Why is that? Because they're out of phase is not quite correct, but they will allow it. You're better off saying they're anti-phase. So one's going up while the other one's going down. Okay, and how do you get that? Well, it's an extra half wavelength, or 1.5 wavelengths, or 3.5 wavelengths, or 5.5, or 12.5. Okay, but it's that extra half wavelength. So trying to describe it is quite hard. So this idea here, you could actually just do a little bit of maths. You could, if you're quite happy with series and things, what you've got is a number of extra wavelengths, however many times. If you do it by half wavelengths, that always works well. So half wavelengths, that would give you an even number. Add on 1/2 wavelength and it'll always be a bit off. So you could use that, or kind of just go for the hope that they'll give you the mark with an extra half wavelength. Okay, so either or. That would be a very mathematical approach to the answer, but you know, most of the marks you can get from describing the constructive, because that's easy to describe the last bit, and then part of the destructive. You could say conversely, you know, it's gone that extra half wavelength to therefore be out of phase, anti-phase. All right. Now, surprising number fell down with this. It is the equation for two sources, which is exactly the same idea as having two slits. Okay, so your equation that you wanted was actually just straight off the data sheet, and we're trying to find out the separation of, there we go, so loud spot to the next one. So a full fringe distance, which on your equation sheet, if you go back, is x. So x equals lambda capital D distance, so big distance, divided by a. Okay, in your data sheet, lambda equals xa over d, so rearrange it. You're trying to find x, so get into the practice of rearranging for the thing that you are trying to find, okay, which is x. And if you put the maths in, then you can get everything working fine. So that is 0.2. This doesn't get the mark on its own, but getting it into the right order does usually give the mark. Okay, big distance is 5. Okay, and you've got your wavelength of 30 millimeters. So again, don't forget it's 30 times 10 to the minus 3, or if you like fractions, you could do it as 30 over 1,000. Personally, I don't like that, but some people can work with it. Okay, so I would go with 30 times 10 to the minus 3, and again, hopefully you've noted that in the questions. Okay, so make sure it's there. Excuse me, there's a lot of changes going on. Right, okay, those are the maths. That will pick up an awful lot of marks. All the way down to here is only you know, not a lot to go in. That's quite hard, but that's 7 marks. That's a big chunk. However, the easy bit is at the bottom, okay, and this on its own was worth 6 marks. And the reason a lot of people went, let's say, went a bit skew with it, is because they ignored the question. So all you're doing is saying what you see, okay, on the position and the intensity. So a lot of people had right answers but didn't mention both, and that's why you've got 2 marks for each one. Okay, so some people mentioned it in some parts but not others. You need both. So amplitude doubles. Okay, now if we think about this, it's all in the maths. Okay, amplitude is not in there, so you cannot think about that. And this is one thing that caught a lot of people out at the end. Amplitude, okay, squared is proportional to intensity. That unfortunately is a fact that we'll work with. We'll eventually, next year, near the end of year 13, we'll look at why, when we do AC/DC circuits and so on. But basically, yeah, the amplitude of the wave, not doubled, but actually if you double that, you'll get 4 times the intensity. So, double the amplitude, intensity times 4. Okay, that's your first answer. Put it in words, or just say amplitude becomes, or you know, with as a squared proportional to I. That will be a perfect answer. Okay, that's your intensity. The position, well, none of those numbers have changed, so you can literally just say x is constant. Okay, the pattern itself doesn't change, it's just it all gets brighter. Now for the others, you're just changing the actual transmitters. Okay, so if you separate the transmitters, some people are saying bigger and smaller, not by quite specific enough, because it's actually giving you a value there. Okay, so if that distance halves, then that one must get double. if you want to put them together, might be easier. So AX equals lambda D, one gets twice as big, the other one must get half as big. So what we've got is the value for, let's say for X, the separation, okay, sorry, the position, so these positions, X will double. And secondly, okay, you move them further apart, will it really change the intensity? Not much, it's not in the equation, so intensity is constant. And down at the bottom, again, we're not actually changing the loudness of the speaker, so again, intensity is constant. And some people got a bit weird with this, because what they did was basically swap the leads over in the back of the speaker, so one went in as the other one went out. You're still going to get all that rippling effect, yeah? It's just that those, instead of being that distance, will be in the gaps in the middle. Okay, so you've changed the phase of them. You've still got the two waves. Okay, so the key with that is that in our positions up here, they're all going to travel slightly further from one of the speakers than from the other. Okay, so basically they are going to change position. That, a couple of people wrote, not quite precise enough. So if you put they swap position, that's very definite. Okay, of you know, bright or loud, etc. Position of loud, quiet fringes, or spots, you know, if you prefer something like that. Let's go with that one. So yeah, they're going to swap over. You just change the phase. The sound is still there. It's not going to change the sound. It's just going to change where it overlaps. Okay, so that can confuse a lot of people, because again, I think you're not thinking about what's happening here. So if you can visualize it, you're not stopping it, you're not turning it off. This one here, you are just moving them apart. Okay, so you're still getting your ripples spreading out, they're still going to overlap, etc, etc. But this is one of those things to try to remember. It is a little factlet that we'll use every now and then. It does appear quite a lot. Okay, next bit, generally good, much better answer. The crucial bit here is some people were going off on a tangent talking about energy and stuff like this. What they're after for this, you've got a closed end tube bouncing at the end, so our reflection at the end, and what we've got is the stationary wave is formed. So you've got a stationary wave, great, it fits in terms of wavelengths. But what you haven't got, that a lot of people did, is explain how it's formed. How does it get there? Okay, so your key point is wave reflex. Okay, let's call it A at A. Why not do that? It saves some time. It's much easier. So wave reflects at A. Then what happens? It comes back. Well, the crucial bit is that idea that we are working on two waves still superposing, but of course they're the same wave reflecting back and forth, or more being created but one reflecting back. So the key is, and again, important words, some people said bounced back. Can't be more scientific, guys. Reflected wave. And again, it just adds up, so I would think about interfering. It all gets a bit confusing, so just keep going with the general. Superposes with, you know, new wave with the speaker wave, speakers wave. Okay, that makes more sense. Okay, so it's that bit, the reflected is superposing with another one. And then what you're saying, as it says, is that forms the process, but it doesn't tell what you're forming. So how is a stationary wave, the picture that I've just shown you, forming? So to produce, and that's all we're after. What does it actually make? What do you observe? So producing nodes and antinodes. Okay, so that's it. And again, keep thinking, you know, it's like a bullet point thing. You've got 3 key points there, okay, for 3 marks. So there's a little bit of a pencil I cut off here. It shows you should show clearly. It's back to our quality written communication. This happens, then this happens, then this happens. There's an order of it. So think of the first thing that happens. Most people got that, and then it went a bit vague for the rest of it. Okay, these ones should be fairly straightforward. Okay, most of the questions we've done have been quite hard about this, but this isn't actually that. It says describe the motion of the air. Okay, and some people go, oh, nodes and antinodes. No, how is it moving? Okay, so what we're indicating with this is we have this wave, but what is actually happening in the wave? What's the movement doing? So here, for example, we've got a big vibration. Here we've got no vibration. That's the bit that matters. It's not about fancy terminology. It's describe how it moves. Okay, so the crucial bit as well is it asks at certain points. So here you've got your maximum vibration. Great terminology, get your terminology. So max, so at 0, there we go, at 0, or at position O, you've got max displacement. No, again, displacement's always changing. Sometimes it's 0 because it's vibrating back and forth. So maximum amplitude. Okay, at 0.2, it's a bit less. So amplitude is smaller. Notice not displacement again, because again displacement changes with time, but the biggest displacement, that is what you've drawn here, or what is drawn here, is a bit less than, again I'll try and always make it a bit clearer, so not just smaller. Smaller than what? Smaller than. Okay, that is a crucial little, it's a comparison to at 0. Okay, and then actually you got a mark for saying, or sorry, you got a tick for saying it's a node, but at 0.6 no movement. Okay, it's about the motion of the air, it's not moving. So max amplitude of vibration, of movement, of, you know, of air. Okay, vibrating. I'll stay with vibrating, it works good. But well, sorry, but yeah, it's that's the important bit. Okay, now this one, again, a little bit of a trick. I think they did that on purpose, but it's not a trick, it's just reading the question. So some people describe this, it doesn't want to know about 0.6. It's saying here, here, and here. So again, at 0, we've got exactly the same. Don't do a ditto, but you know, that's what we're saying. We've got a maximum amplitude. 0.2, again, you've got no vibration, just like it is there. So no movement. Okay, or no vibration if you prefer. And then at 0.4, okay, notice again, read the question, don't just jump in with both feet. Again, it's max displacement, and that was enough to get 2 marks. I should say for both of these you have to get 2 of them right to get 1 mark. Okay, so you get 3 of them right for 2. A good answer is out, or anti, even better, anti-phase with 0. Okay, the 0 position. So that's a great answer. Okay, how is it actually moving? Where it's moving down as that one moves up, for example, or side to side. Again, this is a graph. It's not actually physical movement of air, it's representing the movement of air. Yeah, but it's doing the opposite to what it is at the beginning. So it's always worth mentioning phase. Phase is a useful thing to slot in. It could be worth marks on its own. Okay, and then it kind of went quite well here. Some people got a bit mixed up, and it did fall down a little for a few people. End of the tube is now open. So if we've got no reflecting surface at 0.6, you've got a maximum. Where it's loud, it's maximum. It's going to be loud where the speaker is, obviously, because the speaker is loud. And at the bottom, it's going to be loud if you put your ear there. So that's what we're after. Okay, and that was, with a idea of frequency, that was an easy 3 marks. 2 marks just to make it cross over better than mine. So actually, it's worth putting a mark in and making it go through there. Okay, so that would be a better answer. You know, they want it to be quite precise. Don't just do a random scribble like I've just done. If you go over on top, that should be fine. Okay, but put a mark. That's worth putting. Make it really clear if you want. Anti-node, great. Okay, so frequency is different from that because that is now shrunk to halfway. So your wavelength has got half as big. Okay, it's shrunk from 0.6, that node. Excuse me, that's a node. What am I saying? Shrunk from 0.6 down to halfway. So therefore, if your wavelength shrunk by 2, you've gone to 2 times f0. Okay, so again, compare. They're on different pages. They might be on opposite pages, but compare them because it's now opened. You've got to change. So how does that change compared to what you had before? And I should point out, this is the fundamental. So again, the longest wave, the lowest frequency that will fit the gap. Okay, if it was the next harmonic, you'd have 2 nodes. Third harmonic, 3 nodes, and you just keep adding nodes. Okay, but usually it's the simpler ones. And then question 4 was quite tricky with a lot of things, except a lot of people get this wrong, and this wasn't tricky. Okay, so crucially, they have the same length, the same scale. Okay, scales upside and so on. Check what it is. It's time in milliseconds. Okay, not meters, not seconds, it's not wavelength or anything like that, a length or anything like that, it's time. Okay, so similarity, same time period. Okay, some people put wavelength. It doesn't tell you about speed, so you can't really tell. You can't see speed from this, so you can't really tell, but you could have time period, which of course 1 over time period gives you frequency, so that works. The different height, so amplitude, or most obviously that's going up when that's going down. 2 people wrote that. That is not scientific terminology. Okay, so they have a phase that's different. Okay, so there's a phase difference, but you've already got that. So the difference is they are out of phase. Okay, now that is important because it links in with this. So this was an easy 2 marks if you just went, yeah, they've got the same frequency. They're going up and down at the same moment each cycle, not necessarily the same as each other, but the peak equals the trough, the peak equals the trough, that peak equals that trough. You know, they're not sliding along. So yes, on its own doesn't get a mark, but if you put the reason with a yes, you've got 2 marks. Okay, so it's a big jump thing because phase is constant. Okay, then it gives you the speed, so perhaps this is where people use this to fill in the top answer. But so we've got our speed, determine the frequency. We know that velocity equals frequency times wavelength. Okay, so we want that, we have that, and we need this, but we don't have that. Ooh, hang on, because we don't know its wavelength either. So it has to go in this order: frequency, and then, and hence, and then the wavelength. Okay, so first things first, frequency is 1 over time period. Okay, excuse me, missed that. So the time period is time to do 1 cycle. It is 3 milliseconds, not 3 seconds. Okay, so equals 1 over 3 times 10 to the minus 3, and if you do that, dead easy, it comes out 333 hertz. Okay, you need the unit there. The answer is actually only two significant figures, so it's 330 on the mark scheme, but they will allow that. And then mu, stick it in there, you've got that, you've got now the frequency, and you can work out the wavelength. Okay, so not hard if you check the information. Most people lost that. Okay, lost it because they didn't look at the graph properly. I should just say, just in case, again, we got a distance, we got x. Please notice it's in micrometers. And then the last part of the question was tough. It's designed to be tough. Okay, so most people actually got these two right. Okay, so at point P, some people say, where's P? Well, just go back and look. At a point P, so at a point, random point, these are two waves meeting at that point. Okay, so all they're after is determine the displacement of the two waves. Okay, so if you're looking for those at point P, they superpose. Okay, determine that. So what we're looking for is at 1.5 milliseconds. You read it off, and what you've got is they're both at 0. So 0 plus 0, it's worth putting that just to make clear, equals 0. Fine, no problem. Vast majority of people got that. If you do it here, okay, for 2.25 seconds, you've got a maximum, and you've got that one. Okay, now most people did get the right answer. What they didn't do is the answer basically is 1, all right, but 1 on its own is not very scientific. Never, ever, ever, ever do a one significant figure. Okay, so what they're actually after is 1.0 micrometers. Okay, so significant figures, without that you won't get that mark. So do not do a one significant figure answer. 0, it would be a bit odd to do that. 0 is an exception because 0 is 0 is 0, but 1 on its own, is that near 1? Is that exactly 1? You know, we can't tell unless you put significant figures. Okay, so that's really, really important. Okay, and then this bit some people fell down on, and it is tricky. So back to that little fact again, the intensity is proportional to the amplitude squared. Okay, so what they're after with this one is this the amplitude of one wave. So just be careful, you're in a separate section. Some people seem to have added the two together and used that. No, so after the amplitude at for that wave on wave T alone. So again, just check back. T 2.5 is again clear as mud, unfortunately, on this graph. So do count it out, do draw some markings and so on. So 2.25. Okay, we've got 3 there. Okay, so that is 3, but we don't know the actual value for the amplitude, well, sorry, the amplitude and intensity, so we can't get an equal sign in there, so we have to compare it to the other one. So S at that same point, which is amplitude, excuse me, squeeze in, of 2, okay, basically you're comparing 3 to 2, so that's your amplitude compared to the amplitude of S, if you wanted to put that. That's right, amplitude of T, and you square it. Okay, so that is what it is. But it's a hard question, but you do need to do that. And if you've done that, if you've learned that, it will probably stick with you. Okay. Now the last one, if we're looking at how it compares for both of them, then what we're doing is, as it says here, the resultant wave, you're adding them together. Okay, so what we just need is simply amplitude 1 plus amplitude 2. Okay, that will give us our resultant amplitude, which will be 1. If you want to be really fancy, plus or minus 1, because it's varying by 1 all the time. And so compared to that on its own in terms of I, that original intensity, okay, then what we need is 1 over 2, because that's our initial I amplitude, and again squared. Okay, and you get what you'll find is half squared is 0.25. Okay, now basically it's 0.25 intensity, lots of intensity, but 0.25 on its own will work. Little bit of a tricky one because they didn't actually put this in the mark scheme, but if you did manage it, okay, intensity is that idea of watts power per square meter. Okay, so watts to the meter minus 2. Okay, some people got a mark from that, but it had to be a really good attempt at the answer to get it, so it wasn't in the mark scheme. Bit of a strange one. I didn't knock you down if you didn't get it. All right, so tricky test in lots of ways, but particularly with standing waves, when you're looking at a lot of the questions, it's all about just using the terminology and joining the terminology together. So back to our original learning points, terminology, and what is the question asking you for. So in particular, that one there where it asks you to describe the motion. An awful lot of people didn't. They went off on a random answer about nodes and antinodes, etc. That's not answering the question.